Advanced Math Lesson 31. Part A is about symmetry. And when a graph or a function is symmetrical, then every point on one side of the axis of symmetry is paired with a point on the other side of that axis that is the same perpendicular distance from the axis of symmetry. So right here we have a parabola, and the axis of symmetry basically you think of as a fold line. If we were to fold our paper on the y-axis here, every point on the left side of the graph would match up with the corresponding point on the right side of the graph. This point is one perpendicular unit from the y-axis, and so is this point. Okay, 2 units and 2 units. So visually, you look for a place where you could fold the paper and they would match up. There's also a way to check them algebraically, and for that you would need the equation, and I'm going to go ahead and I guess demonstrate that down here. The equation for this parabola would be y equals x squared, or f of x equals x squared. I'm going to write these with y's. You know, those are interchangeable. If you see f of x, you can write it as a y. Okay, so that if you were to choose some x's, find some y's, you would get this graph. Okay, so to check algebraically whether this is symmetric with respect to the y-axis, so to check for y-axis symmetry, we're going to change the sign of x. And if the resulting equation simplifies to being totally the same as the original equation, then it is symmetric with respect to the y-axis. Okay, and we're changing the sign of x because if it truly is, okay, let's say our x is 1. If we put in a negative 1, we should get the same y value. If we put in a 2 for our x, okay, and then we put in a negative 2, those two should each give us the same y value, so they should be equivalent. All right, so in this one, instead of squaring x, I'm squaring negative x. All right, well, I know that a negative times a negative is a positive, so simplifying that, I get this, which is totally the same as the original equation. So yes, it is symmetric with respect to the y-axis, just like it looks like it is. Okay, then on this one, this would actually be x equals y squared. It's like a parabola turned on its side. This is not a function. It would fail the vertical line test, but it still has symmetry. It's a relation. It's a set of ordered pairs. So this would be x equals y squared. Okay, and it looks like it's symmetric with respect to the x-axis. Right, there's our axis of symmetry. 1 unit away, 1 unit away, 2 units away, 2 units away. Okay, that same perpendicular distance. And to check for x-axis symmetry, I'm going to abbreviate this a little more. For x-axis symmetry, we're going to change the sign of y. So it's the opposite one. And it's for the same reason. You know, if we have y could be -1 or +1, x is 1 in both of those cases. So it should turn out to be the same equation if it truly is symmetric with respect to the x-axis. Okay, so now instead of squaring y, I'm squaring -y. And same thing, that simplifies to this. Totally matches. Yes, it is symmetric with respect to the x-axis. Now I also wanted to show you when it doesn't work, but we'll get to that. Okay, so this one is x squared plus y squared equals 3 squared technically is the standard form of the equation. I'll go ahead and write a 9. Okay, that would be the equation of this circle. All right, so, and it's because this is the radius squared, 3 units. Anyway, just looking at this, just a visual analysis of this, we can fold on the y-axis, the 2 halves meet up. We can fold on the x-axis, the 2 halves meet up. And then we also need to talk about symmetry with respect to the origin. And to check it visually, you could turn your paper 180 degrees. And if the graph is totally the same as the original, then it's also symmetric with respect to the origin. Okay, if I turned this parabola 180 degrees, it will be opening down instead of up. If I turn this 180 degrees, it'd be opening to the left instead of to the right. So not with respect to the origin. This was only y-axis, only x-axis. This is all of them. Okay, and since we already have demonstrated how to check for y-axis symmetry and x-axis symmetry, we're going to do the origin for this one. So, for symmetry with respect to the origin, we're going to change the sign of x and y. And if it comes out the same, then it really is. Okay, and again, same kind of reason. Okay, so 3, 0 is a point on this. Okay, and turning it 180 degrees would be saying that negative 3, 0 should be on this as well. And you could pick any other point on the circle, and if you spin it 180, if you choose some point here, that means the one over here. Signs of x and y have changed when you move over to that opposite quadrant. So anyway, demonstrating with this equation, we're squaring negative x, we're squaring negative y. Okay, x squared plus y squared equals 9. It is exactly the same equation, so yes, it is symmetric with respect to the origin. If there were room, we could check for x and y symmetry also, and we'd find that it's all of them. Okay, now below here we have some other graphs. Okay, and they have, each of them has at least one axis of symmetry, but it's not y-axis or x-axis. Here the line of symmetry will be right here. That would be x equals 2. One thing I forgot to mention, I don't know that it's actually in the book yet, but you will need this later. We're going to go ahead and label it now. If a function is symmetric with respect to the y-axis, we call that an even function. I'm just going to write it up there with our parabola. Okay, even function. It's symmetry with respect to the y-axis. Okay, and if it's symmetric with respect to the origin, it's odd. Origin, odd. They both start with an O. And I didn't leave a lot of room there. I'm going to put this, I should put them both above maybe. Okay, so odd function, and it's symmetric with respect, whoops, forgot my seat, to the origin. This one is odd and even because it's also symmetric with respect to the y-axis. Okay. So it's odd because of this. This one's also even. because it has all the symmetries. Okay. Now back down to these on the bottom. We can see this is not symmetric with respect to any of the things we were looking at up above. If we fold on the y-axis, then the same parabola should be over here on the left, and it isn't. If we fold on the x, there should be another one down here, upside down. It's not. If we spun it 180 degrees, there should be one over here. There's not. So it has none of those. It is symmetric, but not with respect to an axis or the origin. Okay, and so we're going to go ahead and, just so I can demonstrate this not working out, you need the equation for this thing, and it happens to be, let's see, y equals x minus 2 quantity squared, which we'll go ahead and FOIL, and then we'll use that one. Okay, so y equals x squared minus 4x plus 4. That's the equation of this parabola. All right, and let's just check for y-axis symmetry. The one up above had that. This one won't. Okay, so check for y-axis symmetry. Remember, to do that, we change the sign of x in this everywhere in the equation. So y equals, and then we square negative x, but we also have minus 4 times negative x plus 4. Simplifying that, we get x squared, and here we have plus 4x, because the negative times a negative, and then plus 4. They both have x squared, they both have a plus 4, but these are different signs. That does not match. It is not symmetric. We could see it visually, but also with the equation we know that this is the case. Okay. Same with this one. If this were symmetric with respect to the y-axis, there'd be a circle on the other side. However, it is symmetric with respect to the x-axis, because you can fold one here. And then what do you think about the origin? Is it symmetric with respect to the origin? Okay, we're going to check it algebraically. So we would need the equation for this one, and this is a little bit more complicated looking. Let's see, the center is here, so we would have x plus 3, whoops, 3, not y, x plus 3 quantity squared plus y squared, and the radius is still 3, so it equals 9. So this would be x squared plus 6x plus 9, but I'll subtract them, so plus y squared equals 0. Okay, this is our equation, and in the future you should get a chance to work with equations for circles, but for now, take my word for that. Okay, so now to check for origin symmetry, I guess that's the one I want to do. We've changed the sign of x and y. So here we have squaring negative x plus 6 times negative x, and then also squaring negative y. Okay, so that's x squared minus 6x plus y squared equals 0. It all matches except that middle term again. They are not the same. It is not symmetric with respect to the origin. If we were to check for x-axis symmetry, we'd find that worked. We can see that it's symmetric with respect to the x-axis. Okay, now, this one on the end, this is a function, and it is not symmetric with respect to the y-axis. Otherwise, there would be pieces here where I'm kind of tracing out. also not the x-axis. If you spin your paper around 180 degrees, you should see that that looks like it's the same. So we're going to go ahead with that and check for origin again, because it looks like it is. Now, you need the equation for this. This one is y equals x cubed. And so here we go. For origin symmetry, we change the sign of both. So I'm just going to write origin, because we're checking that. And so we change the sign of the y, and we change the sign of the x, so we're cubing negative x. Okay, so negative y equals, and when we cube a negative, we still have a negative. That doesn't quite look the same, but you know, if you took a negative 1 times both sides, you're getting y equals x cubed. They are the same. And yes, it is symmetric with respect to the origin. Nothing else, but it is symmetric with respect to that. That would be the end of part B, or part A, sorry, looking ahead. And then we move on to part B, which is about reflections. And you'll find there's quite a bit of similarity between talking about symmetry and talking about reflections. Okay, so you see the same graph on each of these on this side, and that's because for one we're going to do 1 or 2 reflections, and on the other one we'll do another one, because we can reflect with respect to the x-axis or the y-axis. That's the typical reflections that we do. So just to keep it uncluttered, we're putting them on different graphs, on different planes. Okay, so the reason this is going to look so similar to symmetry is we're still changing the signs of our x's or our y's depending on what you're doing. So let's reflect on the y-axis first, I guess. Let's see. The equation for this particular parabola that you see is y equals, okay, so the original, I'll put right above the graph, y equals x squared plus 8x plus 16. Okay, if you pick some x's, find some y's, and this is the graph you get. Okay, so now we're going to make a reflection over here. And every point on the new one will have the same perpendicular distance to the y-axis when we're done. So that's why it's so similar to symmetry. All right, so to do this, we need to change the sign of our x's. Okay, so to reflect on the y-axis, change sign of every x in the equation. So we would have y equals squaring negative x, but then also 8 times negative x plus 16. Okay, so then this now is what we're graphing. And we would pick some x's and find some y's, graph them, and connect the dots. So that's what we're going to do. Trying to decide if I want to factor this first. I guess I'll leave it the way it is. And then we're going to do this. Pick some x's, find some y's. And we know we're flipping this over the y-axis, so I want to choose things like, well, here I see a point where x is negative 1, so how about I pick positive 1? If x is 1, I get 1 squared, which is 1, minus 8 times 1, plus 16. 16 minus 8 is 8, plus 1 is 9, and that's right here. think I pointed to the wrong place whenever I was pointing earlier, but it's right there. Okay, and, well, this is at -4, so a +4 should be my vertex. Let's try 4. Because I know it's supposed to be flipping it to the other side. So I'm picking some key points based on this graph. Okay, so 4 squared is 16 minus 8 times 4 is 32 plus 16. I get 0, just like I'm supposed to. So I have that point. And then looks like -7 gave us 9, so +7 should give us 9. Let's see, patterns. If I go up the same, I should see the same pattern here. Alright, so 7 squared is 49 minus 8 times 7 is 56 plus 16, -40, 49 minus 40 is 9. It worked. 7, 9. Okay, and then I should have had some more curve to it, but there is my sketch of the reflection. Okay, now if we go down here, this is the same parabola, so it's the same equation that we had above. Now we're going to reflect it on the x-axis, which means we take the original equation, I guess I'll write it here again, and we're going to change the sign of y to flip it on the x-axis. Okay, to reflect on x-axis, change sign of y. Okay, so -y equals x squared plus 8x plus 16. But we're used to having just positive y equals something for our graphs. So what I'm going to do is take -1 times everything on both sides of the equation. I get positive y equals -x squared minus 8x minus 16. Okay, so again, I'm going to use the original graph to find some key points that I want to use for my chart. I definitely want to include the vertex and like one other point on either side of it. So, what if we did, it looks like it goes through -2, 4. Let's see. -2, that would be 4. 20 minus 16 is 4. Yes. Okay. So, I'm going to use -2, and now since I'm flipping it on the x-axis instead of 4, I should be getting -4. Same perpendicular distance from our axis of symmetry, basically, from our reflection line. Okay, so if I put -2 in here, I have negative from this negative, and then when I square -2, I get 4 minus 8 times -2, so minus -16, so plus 16 minus 16. I'm getting -4, which I'm supposed to. -2, 1, 2, 3, 4, -4. And when I put -4 in, I should get 0. Okay, so we have the opposite of -4 squared is 16. Minus -32, so plus 32, but then minus 16, that is 0. So there we go. And then, okay, we go to -6. This should give us -4 again for the y. Opposite of -6 squared is 36. minus negative 48, so plus 48 minus 16. Okay, looks like negative 4. So we go right here. I could pick some other points to do a better sketch, but we have something like that. And we have reflected it on the x-axis. Okay, now how do you suppose we reflect with respect to the origin? You notice all the similarity with symmetry. Okay, so if we wanted to do that, we would be changing the sign of both. I did want to point out another reason this is so related to symmetry. There's so many similarities. If we look at that graph as a whole, the two parabolas together as one graph, it's symmetric with respect to the y-axis. If we fold on the y, those two parabola, if I had graphed better, would totally line up with each other. And then on the one down below here, if we folded this graph the way it appears now with both of those, fold that on the x-axis, they should totally match up if I had graphed it better. Okay, so when you graph the original function or relation and its reflection together, that thing is symmetric with whatever axis you reflected it on. Okay, now I believe we are ready for translations. Okay, translations are slides. So, we can slide horizontally and we can slide vertically. So left or right, but also up and down. And we're going to talk about this algebraically as well. So let's get an equation for this. 1, 2, 3, 4. Okay, this is just y equals x squared. Your standard parabola. All right. And let's say we wanted to slide this down 3 units. Okay. To slide it down 3 units, here's what we do to the equation. Okay, because y equals x squared, this tells us when we put an x in, it'll tell us how far up or down the point is, right, the y. We want it to be 3 lower because we're sliding it down. So subtract 3 from whatever you get when you square the x, and that brings it down 3. Well, let's pick some x's and find some y's, and you'll see how that works. Okay, so if x is negative 2, then when I square negative 2, I get 4. 4 minus 3 is 1. Negative 2, 1. That is 1, 2, 3 points below the original point. Okay, from that when x is negative 2 on the original graph. Okay, what about when x is negative 1? When we square negative 1, we get 1. 1 minus 3 is negative 2. Negative 1, negative 2, 1, 2, 3 units below the original. When x is 0, 0 minus 3 is negative 3. 1, 2, 3. See, it's always 3 units above the original graph. I mean, below the original graph. Okay, then we'd have here 1, 2, 3 here, and so on. Okay, and there's my rough sketch. I should have picked another point further out on each side, and I could have gone the whole way up there. But that would be my rough sketch of that particular translation of that function. Okay, we can also translate horizontally, left or right. Okay, so let's do to slide this, let's go to the right. What, 4 units? Okay, now y equals this part seems, whoops, the original one, not the one I just translated. Okay, so instead of y equals x squared, it's x minus 4. It seems counterintuitive. We're going right, but we need to put a minus here. Okay, so let me just demonstrate the graphing of this, and you will see. Okay, so x and y. Okay, so let's choose, well, let's see, if I choose 0, it's going to be off my grid here. How about 1? When x is 1, 1 minus 4 is negative 3. When I square that, I get a 9. So 1, 9. That is right here. Okay. Let's try when x is 2. Okay, when x is 2, I have negative 2 squared. That is 4. Okay, when x is 2, well, that's for the original graph. Okay, when x is 3, 3 minus 4 is negative 1. Squaring that, we get a 1. 3, 1. When I choose 4, 4 minus 4 is 0. 0 squared, 0. Okay, and if we go to 5, 5 minus 4 is 1. It's coming back up. 5, 1. Okay, it's going to be the same shape. It's just been moved over. And that means up here, here. This is getting pretty busy. I should have moved it over further. Okay, so this, here is the one we moved down, y equals x squared minus 3. And here's the one we moved to the right. Okay, the vertex is still on the x-axis, just like the original. But look, 1, 2, 3, 4 units to the right. And I know it seems counterintuitive, but when you're going right, it's minus. When you're going left, it's going to be a plus. Okay. Now, this one is a square root function. This is y equals the square root of x. That's the original. And we already moved one down. Let's move this up. Let's move it up 6. To move it up 6, that's just y equals the square root of x, and then not under the radical, we have a plus 6. Okay, so if we put a 0 in, let me make my chart, whoops, x, y. Okay, 0 plus 6 is 6, so it's way up here. Square root of 1 is 1, plus 6 is 7. So we're here. Okay, then I want to do things I can take the square root of. So let's go to 4. Okay, square root of 4 is 2. That gives us 8. That's here. And then I would go to 9. The square root of 9 is 3. Add 6 to that, we get 9. And that's way out here. Something like that. Okay. Then we should also do one where we shift it to the left. Okay? So now we're going to translate it to the left, and I'm trying to keep things from being cluttered. So let's go left 7. Okay? So now we're going to go left 7 units. And so that means we do y equals, and then under the radical, we're going left, so it's plus. Remember, it seems counterintuitive. Seems the opposite of what you would think. So x plus 7. Okay? Taking the original, and we're going left, so plus 7 goes under the radical. And then we're going to pick some x's, find some y's. And making sure it's things that will come out nicely for us. So I think I probably want to try -7. Okay? I don't want to go below -7 because then I have the square root of a negative, and I can't graph that on a Cartesian plane. But -7 plus 7 is 0. The square root of 0 is 0. So we're right here. Okay. Then let's see. We should probably do -6 would be fine. Okay, -6 plus 7 gives us 1. The square root of 1 is 1. All right, then let's also do, I get a 4, -3 would be good. Okay, 7 minus 3 is 4. The square root of that is 2. So -3, 2. And how about, let's see, that gave me a 4. I wouldn't mind having a 9. So how about 2? 2 plus 7 is 9. The square root of that is 3. So then we're way over here to go up to the 3. And then let's connect them as a curve. Okay. And there we go. There we go. This one just moved straight up. That was our vertical translation, up 6. This was the horizontal translation. It just slid it over. We went over 7 units to the left. And that is how you do the translations. At some point, you'll be doing where things are combined. You might have a reflection and a translation. But for now, I think we're just going to be done with these notes. Enjoy the graphs.